Perfect. Then, yeah, let's directly start. Thank you for giving me the opportunity to give you a first introduction of what we are currently doing within the EU-funded ENSUREAL project. And yeah, my part within this project is to look a bit at big scale, how it did maybe look like then in real life, in industry scale. And so that's the reason why I started with a mass and energy balance. So first of all, ENSUREAL project is about the Pedersen process. For the one you maybe hear this process the first time. So I want to start with a first quick introduction of the process itself. So we have three main parts within the project, which means that's the hot section, where we have a submerged arc furnace, where we add the feed material, limestone, bauxite, and coke. Limestone, there's some treatment can be done, and we melt it at the first stage. So there the iron part of the bauxite can be removed. Afterwards, we have slag treatment, means casting cooling at the beginning. If we have the right composition, then the slag might be self-disintegrating. After this one, the slag is then milled to the final leaching conditions, and so that the leaching can be done. The special thing within the Pedersen process compared to the Bayer process is that we are running it with sodium carbonate. So we have here between the leaching and precipitation a sodium carbonate circle that extracts the alumina from the slag. The remaining phase of the process is the gray mud, which is mainly calcium carbonate, which then can be used as fertilizer. And so, yeah, we have a different and more nicer and easier to treat byproduct. So the aim of this project is not to treat the bauxite residuals, or maybe in another version to treat the bauxite residuals. So the basic idea, if we start with bauxite, is that we have no bauxite residuals, more or less. And yeah, after precipitation, the alumina hydroxide is calcined, and we produce the final alumina. So that's the quick step into the process. So now a short step into mass balancing. Last conference was in Greece, so I thought I should start with the Greek. The old colleagues from the 4th century before Christ already says nothing came from nothing. So that's a bit different to financial industry. But we also have the law of conservation of mass, who was discovered a bit later. And the main conclusion of this is that what comes into a plant also has to leave the plant somewhere else. And this basic principle behind the mass balance helps a lot to understand the process better, to understand the process streams better, and then go step by step more into the details and find from the chemistry and the streams, then finally process equipment that can be used. So what's the aim of this balance? It's transferring the generated lab data to industrial scale. It's to get a feeling about the process streams and the required process equipment. And also the advantage to having an automated system is that you can somehow handle the butterfly effect. Let's see, so if you change a small input parameter, this maybe has a big effect of the other side of the total process and plant design. And finally, when everything is working well, it helps us to get data and numbers for the investment of a possible plant, and also what's the operation of the plant. So here a short introduction of the background. So within this mass balance, I used the HSC software tool from Autotech, and the aim was to having a flexible tool that can be adjusted in parallel to the running tests and experiments, and always to get a first feeling of the final design capacity, which is 500,000 tons alumina per year, and we are currently assuming to do that within 8,200 hours of uptime of the plant equipment, so that we then get a feeling of the sizes. As mentioned, feed material for Pedersen is bauxite, coke, quicklime. And here are the basic concentrations and compositions of the materials which are currently in the model, and which can for sure be adjusted as needed. So here again, giving a first introduction of the balancing model, or how is the structure behind. So it's built in 3 levels. So we have the top level with covers smelting, hydro, and calcination. My personal part is more the hydro part, so that's the reason why I'm looking more into this hydro streams, where I have again then the digestion, the leaching, and the precipitation of the alumina, and besides the washing steps of the produced byproduct gray mud, but also the washing of the alumina hydroxide. So washing is a big issue, let's say. So it's a countercurrent operation and backflow washing, because you don't want to lose too much of your materials, of your chemicals during or over the takeover point. And so it's important for the efficiency of the project or the process to do the washing properly. So the model also allows us to use a different number of washing and leaching stages. This can be adjusted in the model however we want. So we can say 3, 5, 10 washing stages, and then finally we get the values back to evaluate and see what was done. So showing you first values or data, what 500,000 tons plant would look like, more or less. So the ore, the bauxite, it's the shown composition is around about 115 tons that has to be added to the smelter. Here it's currently mentioned limestone, 141 tons to the smelter, which can also be quicklime, so which would mean then this number is reduced, and the CO2 is also reduced to have the same principle that what goes in goes out. At the current assumption, we would produce 18 tons of pig iron and 110 tons of aluminum hydroxide in wet conditions. So that's the main basic streams, and as you can see within the balance, we have much more data available. So I really know the moisture, trace elements in the water phase, and also the solid phase and the composition of the gray mud, for example. So going from the first level to the second level, here you see that the core, or the biggest mass and material stream, is between digestion and precipitation, where we are circulating bigger amounts of solution to keep the process running, and the slag and the outflows are smaller. And so it's important, or the important knowledge of that is that this core circle within the process defines at the end of the day the size of the plant, the costs of the equipment, and so on. So here you see again the more detailed composition of the sodium aluminate solution, and it's most part is water, and we having the sodium and sodium hydroxide are in a smaller range. So it's just 15% are the chemicals which doing the job, and the remaining part is the water, which keeps the system running. So based on this data, or the mass flows shown, it's also possible to do case studies within this balance, and to compare different designs of a possible later plant. So one important part, as shown here, the GM means gray mud moisture. So at the takeover point from the leaching to the washing, I was looking at different moistures which are transferred to the washing stage, and which directly means the runover of materials is changed. Then I also changed the number of washing stages within the case study. So I have 6, 3, 10, and 5. And this moistures mean 65 and 20% are meaning here the first stages of thickener, where you pump just a slag from thickener to thickener, which means you have a very high moisture with 65%, and the last stage is then a filter press or so on, that you have then the 20% of moisture. And same is valid for the alumina hydroxide washing. So by doing that evaluation, you see the amount of sodium hydroxide, sodium carbonate you are losing per hour within that case. So the best case is that 7 tons sodium hydroxide has to be replaced, which is then the sodium silicate in the gray mud. And by the other design versions, you require more sodium hydroxide. So this amount is not that big issue. You maybe think it's just 200 kilo an hour. But assuming that sodium hydroxide has a price of 230 euro per ton, it makes in the year really a difference in the operation costs. And to know this difference in the operation costs finally would then allow you then to make a decision how much thickeners you use. So that's different case scenarios that can be investigated. And so more or less coming to a quick end. Also, when we know the process streams, it's also possible to do with pretty easy calculations to get the first feeling of plant dimensions. So I took here.
We're running out of time. Please, if you can wrap up time.
Yeah. So yeah, it's last slide is coming. So knowing the streams, you know then how thick the pipe has to be. So the conclusions are mass balance is an important tool already during conceptual phase to get an idea what lab tests will mean then in a bigger scale. It also helps you directly during lab phase if you look at the bigger scale to identify dead ends. Maybe not everything which is possible in the lab will be possible in a plant. Yeah, and running different case scenarios helps you to get a better understanding and pushing the plant development forward. So, principal, that's it. Thank you a lot, and I hope you enjoyed.